big version. So, lecture 3.6, state space model of a rotational mechanical system. So another example with a rotational mechanical system. For the rotational mechanical system shown, find a state space model with outputs being the spring torque and the angular momentum of the moment of inertia. So let's take a look at this system for just a minute. We've got an angular velocity source that is being applied to a node. We've already modeled the system. So this schematic is already something that we're approximating the system to be. So probably this is a relatively light, relatively short, relatively inflexible bit of shaft here that is being, I guess, that the source is being applied to. And that is attached to a drag cup, which is a type of damper, right? An inline damper that couples the two sides of the shaft, the side that the angular velocity source is being applied to, and then the side that the flywheel is on. So that's what's next, is this flywheel, or angular moment of inertia, J, and it's being supported by a bearing B2. As you guys will learn in machine design class, you really will never support a shaft with one bearing. You're going to want to have at least two, but we could model two bearings in a lumped parameter model as one bearing, as long as they're attached to the same piece of shaft. So if like you have two bearings, like one on one side of the flywheel and one on the other side of the flywheel, we assume they're at the same angular velocity on both sides. So you can just lump them into a single one if you want. You could do them separately, or you could put them together. It's up to you. Yeah?
No. Sorry, I answered my question.
Okay. Good. There's the bearing, and then there's this spring that is, so maybe that's a spring, an actual rotational spring, or maybe it's just like a long, flexible shaft, okay, that has a spring-like quality to it. So that's attached to ground. So let's think about, there are a lot of different real mechanical systems that might fit this model, but one that is, I think, a kind of a fun one is that if we thought of this thing as being a velocity measuring device, if you wanted to measure the angular velocity of the shaft that is being connected here, then this would be a kind of a cool way to do it, because B1, this drag cup, when the angular velocity of this side is 0 and the angular velocity of this side is 0, there's going to be no force or no torque transmitted, right? And if it's going really slowly, there's really no torque being transmitted, because the torque that it transmits is proportional to the velocity, right? So, but if you start to speed it up, if you start to speed this side up, say this side's going, not quite as fast, so this one starts to go faster and faster, and it starts to transmit more and more torque. Drop across this is going to be greater and greater, and this angular moment of inertia is going to want to turn, right, in the same direction that omega s is going. It's going to want to turn, but its turning is going to be resisted by the spring, assuming it's not like bouncing back and forth. But if you're just like thinking of this like slowly ramping up the speed, the flywheel will turn. So you can imagine your input like speeding up, and your flywheel is turning a little bit more, a little bit more, a little bit more. The more torque that gets transmitted here, the more torque the spring needs to resist that, which means that it has to be displaced more and more, right? Its angular position is going to be greater and greater. So if, for instance, you were to look at J and you wanted to make a speedometer out of this thing, you could have a needle painted on the flywheel, and then you could have like some, I don't know, clear plastic cover on it with calibrated angular velocity demarcations. So it's essentially a type of speedometer. The faster you're going, the more this needle will turn, right? The more the flywheel will turn. So it's sort of like an old school, purely mechanical way to measure the velocity of a shaft. So kind of cool. So I just want to I know that we don't always spend a ton of time talking about like the what types of systems this could model. A lot of times we start with the schematic. So it's good to think about like what kind of things would this could this be used for, or what kind of things might this be a model for. So I think that was a fun one. So I wanted to stop and like chat about that. I think measurement is a really cool topic, and yeah, I geek out about it, I guess. I don't know. So let's do some analysis on this. We needed to first 0 point A. We need to do an assignment of, so assign the coordinate arrow, right? So the coordinate arrow, we might as well draw it in the direction of the angular velocity source, which is always our preference, right? If we can. We like to do that, but we don't have to. And in some cases, you might have multiple sources, and they might be pointing in different directions, and you just have to choose a direction. Okay. Now, we are ready to draw our linear graph. So we're definitely going to have a ground, and we need to choose the nodes for the system. It's always easy to identify the node associated with a moment of inertia J, so there's one, J, and we also have this angular velocity source, which is going to specify a distinct angular velocity, right? So that can be drawn in here, and that is omega s. The direction of the arrow for omega s is what? Away from or toward the node of application? Away from the node of application. And the reason for that is it's an across variable source. Okay, that's one thing. The coordinate arrow is drawn in the direction of the cross variable source. So therefore, our convention states that we must draw the arrow away from the node of application. Yes?
Current would be the opposite, correct?
Correct. Well, torque in this case, because we're doing the rotational mechanical system domain, so the through variable is torque. So if this was a torque source and we had the coordinate arrow drawn in the same direction, it would be drawn toward the node of application. So exactly the opposite. So it depends. So it depends on a couple things. It depends on the direction of the coordinate arrow relative to the source. It also depends on what type of source it is. Is it an across variable source or a through variable source? So omega s is an across variable. Angular velocity is an across variable. So it's an across variable source, and we have to draw it away from the node of application. This is in that really long and tedious lecture that I just uploaded to YouTube instead of going through it in class because I don't remember. I think I was traveling or I was sick or something. Who knows? I'm kind of flaky like that. You just never know. I'm kidding. I'm not flaky at all. So we've got we have these several elements that are going to be coupling these nodes together. So B1 couples the angular velocity source to the moment of inertia J. So we draw the arrow to the right because that is the direction of the coordinate arrow. So if you follow the coordinate arrow from left to right, you hit this node and then you hit this node. So B1, our convention says to draw in that direction. We have a connection to ground here with B2. So let's draw that guy in here, B2. And we have another, and we always, if it's connected to ground, we'll just draw it to ground, right? And finally we have K, our spring. We draw it to ground for two reasons, because it's connected to ground, and because from left to right you go from the J node to ground. So it's got two reasons to draw it that way. Okay, so now we're ready for our 1.A step, which is the normal tree, right? So let's get another color or a highlighter or something. And we go down the list, right? A cross variable source is our first. Angular velocity is an across variable for a rotational mechanical system. So omega s, yeah, you're supposed to do the nodes. I always skip the nodes. It's not that you should skip the nodes. It's that if you do all the branches and you just say, okay, all the nodes are in there, then that's okay. So you're right. I should just get better about this. I'm not very disciplined with my node selection. So okay, so all the nodes are in. Omega s, the angular velocity source. A-type energy storage elements are next, right? So there's our J, our moment of inertia is an A-type element. So good there. And then it would be D-type, right? So there would be the dampers, B1, B2. But if you select B1, you create a loop. You select B2, you create a loop. Then it would be T-type. If you select K, it would create a loop. So we're done. Great. I'll switch back to the other pen. And the next thing we need are our variables, primary variables, and secondary. So primary variables are cross variables on branches, so omega s and omega j, and through variables on links, so tk, tb1, and tb2. Secondary variables are just the opposite, so ts, tj, so angular velocities are coupled to torques, and then the opposite happens here. Omega k, omega b1, and omega b2. C. 1C. We have our state variables, right? So our state variables are going to be across variables on branches. Yeah.
So are there like the ohm symbol? Is that the same as writing like the W?
So this is lowercase omega, and this is capital omega. We use it in the same way that like you would have like a lowercase w and a capital W. They're just different symbols. So it depends on context. So you could do these all with little omega as your angular velocity if you wanted to. We use capital. The reason we use capital instead of using lowercase usually in these problems is that we are trying to avoid using omega, this lowercase omega, because we use it a lot when we get to so-called the frequency domain or the frequency analysis, which we won't get to this semester, but we'll get to next semester. But it's always very contextual. So little omega is used a lot of times in frequency domain analysis to mean the frequency of the input signal. So it'd be like sine omega t, it's your input frequency. So when we use omega in these problems, and we're later going to use little omega, we want to avoid that conflict that's going to happen. So that's why we use big omega. Yeah. So state variables are going to be, so you look for A-type energy storage elements that are branches, right, that are in the normal tree. So we've got J, which is an A-type, and it's in the normal tree. So we have to take its across variable, which is omega J, angular velocity. And if you want, the other state variable is going to be associated with the T-type energy storage element in the links. So the T-type is K, and its through variable is the torque, Tk. So that implies that the order of our system is second order, n equals 2. Okay. D. So we need to do our vectors, right? So our state vector, input vector, and our output vector. So we have x equals, and then you just create a column vector with all of our state variables. It's arbitrary which order you choose them to be in. As long as you stick to that order, you're good. So there's our state vector. Our input vector, once again, we only just have a single input, so omega s. We'll see some problems with multiple inputs later, but for now, we're keeping it simple. And then y is our output vector, which we said in the problem that we're interested in the spring torque and the angular momentum of the moment of inertia. So we have two values. One is the spring torque, Tk, and the other is the angular momentum of the moment of inertia, which we can call Hj. All right, 1e. You might think that the number of rules that you have to remember for this is just like impossible, but I mean, I know I've been doing it a lot, but no, I feel like I messed up because you guys were looking. But I've been doing it for a long time, but like I can remember them now off the top of my head, and I think that you guys will be able to as well when you get to the exam. You'll be able to move much quicker. I'm like going through all these details. Yeah.
What was
Hj is the other output. So it's the, I say it in the problem, it's the moment of inertia angular momentum. It's kind of a weird, awkward way of saying it. I would go back and say the angular momentum of the moment of inertia J is what I should say. So it's just a little awkwardly put. Yeah. Yeah, it's a good question. So like the first couple you do are going to take a while, but then once you get into the flow of it, I think that you guys could do like a second order like this in like 20 minutes, 25 minutes probably.
So with that being said, what do you expect on some of these types of questions?
You could think of it as being, I might not give you two whole ones, but I might give you like one whole one and then like some partial ones and some concept questions, or maybe I'll give you two whole ones. I kind of mix it up, but I don't necessarily expect you to get these done in like 10 minutes, but probably think like 20 to 25, maybe if like for this example, like a second order. The one that we did last time was a bit longer because it was fourth order. We had more equations, so So yeah, I'd expect you to be able to do this one probably like 20 minutes. Yeah.
How do you decide which variables
Yeah. So the rule is that state variables are going to be across variables on A-type energy storage elements in the normal tree. I know, this is a lot of qualification there. But the across variable, which is omega in this case for a rotational system, of A-type energy storage elements, which are moments of inertia, and in the normal tree, or that are branches of the normal tree. So that's J is the only one, and then the other side is the through variable of T-type energy storage elements that are in the links or that are not in the normal tree. So that's why we get TK, because K is a T-type energy storage element. It's not in the normal tree, and so we take its through variable. Cool. So E. Now we are ready for some equations. So we start with the elemental equations. And our elements, remember, we like to start out by listing them in the same order as our state vector, just for fun. It's not really for fun, it's just to keep track a little bit easier. So our elemental equations are d omega j dt. So this is like the Newton's second law analog for rotational systems. 1 over j tk. Or not tk, tj. For the spring, it's the time derivative of Hooke's law, so it's dtk dt equals k omega k. For B1, we have TB1 equals B1 times the angular velocity of B1. And it's essentially the same for B2. TB2 equals B2 omega B2. Oh man, that was a crappy little omega. What is that from? Crappy little hand? It's like a thing. I mean, this isn't even like a Trump thing. Like, this is like before that. Crappy little hand. Oh, it's from Cards Against Humanity. Ha! Yeah, that's one of the cards in Cards Against Humanity. A crappy little hand. I always thought it was hilarious. I don't really know why, but I think it's a great card. I feel like I've won with that card a few times. Oh, word of advice, because you guys are the section that I just say random shit to. Never play Cards Against Humanity with your mother. That is not a good idea. I got conned into this. People were like, oh, it'll be fun. It wasn't fun at all. It was terrifying. Yeah, in-laws, yes, that would also be bad. I just remember that at one point the card that I will just summarize as being BBC was played by my mother, and I was like, shut up. No, this is not okay. I am not interested in playing this game anymore. Okay, that was TMI right there. That was TMI. Yeah, nobody say it out loud right now, please. So there's really no safe conversation about Cards Against Humanity to have in class. I realize that now. So elemental equations, we're done with them. Remember that we do like to solve them for primary variables. The energy storage element equations, we always already write that way with the time derivative on the left-hand side. There are always going to be primary variables that are being differentiated. And then for the B1 and B2 equations, primary variables are the torques, right? So already have them solved for the torques, so we can just say no need to rearrange. Great. So we are on 1F, continuity equations. So remember that we need a continuity equation for each passive element in the normal tree, or passive branch, right? So J is the only passive branch in our normal tree. So we need a contour that intersects just that element in terms of elements in the normal tree. So this contour is a good choice. And we can say that the torque that is leaving the contour, torque J, since it's leaving the contour, it must be equal to all the torque going into the contour, right? So torque B1, TB1, is going in, minus TB2 minus TK is going to be equal to TJ. So J, and we have TJ equals TB1 minus TB2 minus TK. So that's our only continuity equation, so we didn't really need the plural there. 1G, compatibility. Equations. So for these, we need one for each link, right? So K, B1, and B2 are the three that we need. So K, B1, B2. And we've got, so for K, we've got the loop that's created when we include K in the normal tree momentarily is, it tells us that omega K is equal to omega J, right? So omega K has to be equal to omega J.
Are the T's also equal?
Only the omegas. So it's just, so torque and angular velocity are like current and voltage. So if you've got two parallel branches, just like if you had two parallel resistors, the voltage would be shared. If you have two parallel elements in a mechanical rotational system, the angular velocities are shared. So we have omega K equals omega J. And B1, if we were to include that one, we would have the loop that omega B1 equals omega S minus omega J. And finally, B2, once again, we've just got parallel elements here. So omega B2 equals omega J. Sweet. So we have all our equations. So now we're ready to start reducing them down. So in 2a, we're going to eliminate all the secondary variables, right? So you can say eliminate secondary variables. And we can do that by, we're going to just take the elemental equations, rewrite them, but substitute in continuity and compatibility equations as we go. So J, K, B1, B2. What? Aw.
It's always about the same thing.
It's really weird, isn't it? I don't know what's going on. Computers. There's something wrong with them. I don't know what, but there is. Clicking on my face doesn't have any positive effect. Not really sure why I thought it would, but it seemed like a good option to try. Alright, so let's rewrite the first bit of this equation. So d omega j dt equals 1 over j. It was tj, right? That was what was there. But we're going to substitute in the continuity equation for j, which says that tj is just equal to tb1 minus tb2 minus tk. And the k elemental equation says that dtk dt equals k times omega k, right? But we have a compatibility equation for that. It says omega k is just omega j. And we're now down to b1, which did say that torque b1 equals b1 times omega b1, but we have a compatibility equation for that. So omega b1 is just omega s minus omega j. Finally, we have tb2 being equal to b2 times omega b2, which we also have a compatibility equation for, and we can just say omega j. So now we're down to 4 equations and 4 unknowns. We have to get rid of 2 variables. Which 2 variables do we need to get rid of? TB1 and TB2. Yeah? Because omega j and tk are the state variables, so we don't want to get rid of them. And omega s is the input variable. The only 2 remaining are TB1 and TB2 to eliminate. So, to B, let's eliminate TB1 and TB2. So we can do that by, we'll just take our J and our K elemental equations again, and we'll substitute in these expressions down here, because we already have solutions for B1 and B2 down here. It might be something that you have to solve simultaneously, but naive substitution in this case, in these problems, works a lot of the time at this point. Like, not if you start the solution process with your total of 8 equations and 8 unknowns, and then you just start ad hoc stuffing stuff in. That doesn't go well most of the time. You go in circles. But once you get down to this point where you've eliminated all your secondary variables, usually, or I would say often, you can get away with ad hoc substitution and getting rid of the rest of your variables. We only need to get rid of 2, and 2 substitutions is all we need here. Oh, I'm back. d omega j dt equals 1 over j, and TB1, we've got this elemental, or originally elemental equation, but now more complex equation right here for TB1, and we substitute that in for TB1 up there. So we have B1 omega s minus omega j, and minus TB2, which we have another equation for that. So TB2 substitute in again. So B2 omega j. And minus tk. But tk is a state variable, so we don't need to get rid of it. The other equation, dtk dt, equals, look at this, k omega j, we already have it all in terms of state variables. So we don't even have any substitutions to do. So we are ready for the standard form of the state equation. So 2c standard state equations. So remember that they are always, or standard state equation, it's a vector equation, right? It's singular. So dx dt equals ax plus b u. So this is the form we're going for. So let's write dx dt. So dx dt is the time derivative of our state vector. So d omega j dt and d tk dt equals the A matrix, which has to be a 2 by 2, right? It's a second order system. The state vector is a 2 vector, so omega j tk. So it has to act on a 2 vector and return a 2 vector, so it must be a 2 by 2. Plus the C matrix, which has to return a 2 vector, it has to add to a 2 vector, but it has to multiply a 1 vector, the input vector u, which is just omega s. So we're ready now to fill in the first row from this equation, j, so you can think of, we're just like rewriting that equation up here, down here. So what is the coefficient of omega j? It shows up here twice, right? It shows up here and it shows up here. So you get a negative b1 from this term and a negative b2 from this one, and then you have a 1 over j. So I would call it negative b1 plus b2 over j. That multiplies omega j plus whatever the coefficient of tk is, so negative 1 over j, so negative 1 over j times tk, plus there's an omega s term here too, right? b1 over j omega s. And now we've got the second equation, which is pretty straightforward. tk dt here. Well, tk dt. dtk dt. That is a tongue twister. K omega j plus 0 tk plus 0 omega s. Any questions on that? Okay, so now,
Why is that 0?
So these are 0 because this equation that we're transcribing right here, it says dtk dt, so this equals k times omega j. So k times omega j, and then plus, you could say plus 0 tk, oh, that's a big K, tk, plus 0 omega s.
Gotcha. Okay.
Yeah.
So would you recommend that we simplify, like we sort out all the terms in the
Yeah, I mean, it's up to you. If you wanted to just up here, just say this is equal to, and then simplify it down. Yeah, that's fine. It's kind of up to you. Whatever you feel is the most comfortable for you to do it. As you know, I don't mind doing a couple steps without writing down because my finger hurts by the end of the day. It's all out of writing now. But I don't know. I feel like it's kind of your own style on that. Choose your own adventure. So D, output equations. So we're almost done. So our two outputs were TK and HJ, right? So TK is a state variable. So in order to write it in terms of state variables and input variables, we just need to write it as itself. HJ, the angular momentum of the flywheel, J, is by definition J times omega J, right? So omega J is a state variable. So that one's done too. We have it in terms of state variable. So then finally to E, we have the standard output equation, which is always of the form y equals c x plus du, or in our specific case, our y vector we can rewrite if we want. So tk and hj equals the C matrix, which returns a 2 vector, operates on the state vector, which is just x, right? A 2 vector. Omega j and tk. And this D matrix must return a 2 vector and operate on a 1 vector, so it's a 2 by 1, operating on omega s. So to fill this in, from the first equation, we have tk equals tk. So tk equals 0 omega j plus 1 tk plus 0 omega s. And hj is equal to j omega j plus 0 tk plus 0 omega s. Okay. Any questions? Yes?
So your output equations, TK equals and HJ equals J omega J.
Mm-hmm.
Was the J omega J, was that just a known something that you...
This is just definition. So the angular momentum is defined, one way to define angular momentum is the product of the moment of inertia and the angular velocity.
The last part with your standard output, where are you getting the 0 to 1
Yeah, so I'm rewriting this equation in this row. So tk equals 0 omega j plus 1 tk plus 0 omega s. And then hj, there's a j, so this one goes there. J omega j plus 0 tk plus 0 omega s.
Yeah, perfect. Thank you.
Yeah, sure.